Problem 95, Quantum Mechanics. The question is, the dynamics of a free relativistic particle of mass m is governed by the Dirac-Hamiltonian H is equal to c into alpha dot p plus beta mc square, where p is the momentum operator and alpha is equal to alpha x, alpha y, alpha z, and beta are 4 by 4 Dirac matrices. The acceleration operator can be expressed as. Here we have to find out the acceleration operator. First, let us write the velocity operator Vx. Vx is equal to 1 by IH bar, the commutator of x and h. This is equal to 1 by IH bar, the commutator of x and h is already given. This is equal to c alpha x px plus c alpha y py plus c alpha z pz plus beta mc square. Now this can be represented as 1 by IH bar, the commutator of x and c alpha x px plus the commutator of x and c alpha y py plus the commutator of x and c alpha z pz plus beta, the commutator of x and beta mc square. Now let us find out each term. First, what is the commutator of x and beta mc square? This is equal to mc square, the commutator of x and beta. We have the commutator of r and beta is equal to 0. This implies that the value of the commutator of x and beta mc square is equal to 0. This is because the commutator of x and beta is equal to 0. Now let us find out the value of the commutator of x and c alpha x px. This is equal to c, the commutator of x and alpha x px. We have a standard equation for the commutator of a and bc. Using that equation, we can find out the value of the commutator as c times the commutator of x and alpha x px plus the commutator of plus alpha x, the commutator of x and px. Now what is the commutator of x and alpha x? This is 0. Therefore, our commutator becomes c alpha x, the commutator of x and px. We have the commutator of x and px is IH bar. Therefore, our commutator becomes IH bar c alpha x. Therefore, the commutator of x and c alpha x px, that is the first term, that is equal to IH bar c alpha x. Now let us find out the value of the commutator of x and c alpha y py, which is the second term in the velocity operator. The commutator of x and c alpha y py, this is equal to c times the commutator of x and alpha y py. Again use the standard equation for the commutator of a and bc. We will get the value of the commutator as c times the commutator of x and alpha y py plus alpha y, the commutator of x and py. We have the commutator of r alpha is equal to 0. Therefore, the commutator of x alpha y is 0. And also the commutator of x py, we know that is equal to 0. Hence, the commutator of x and c alpha y py, that is equal to 0. That is the second term in the velocity operator is 0. Now let us find out what is the commutator of x and c alpha z pz. This is equal to the constant multiplied by the commutator of x and alpha z pz. This is equal to C times the commutator of x and alpha z pz plus alpha z the commutator of x and pz. Close the bracket. We have again the commutator of r alpha equal to 0. Therefore, the commutator of x and alpha z is equal to 0. Already we know that the commutator of x and pz is 0. Hence, we can say that the value of the commutator is 0. Hence, we can write the commutator of x and c alpha z pz is equal to 0. That is the third term in the velocity operator is also 0. We have already evaluated the fourth term. Therefore, the velocity operator becomes 1 by ih bar c alpha x plus 0 plus 0, and this is equal to c alpha x. That is, our velocity operator is c alpha x. Now, let us find out the acceleration operator ax, that is equal to 1 by ih bar the commutator of vx and h. This is equal to 1 by ih bar the commutator of c alpha x and h. Now we can write it as c by ih bar alpha x, h is c alpha x px plus c alpha y py plus c alpha z pz plus beta mc square. Now let us expand the commutator. This is equal to c by ih bar the commutator of alpha x and c alpha x px plus the commutator of alpha x and c alpha y py plus the commutator of alpha x and c alpha z pz plus the commutator of alpha x and beta mc square. Now let us evaluate each term separately. First, let us consider the commutator of alpha x and c alpha x px. This is equal to c times the commutator of alpha x, then alpha x px. We can use the formula, the commutator of a and bc, so that our commutator becomes c times the commutator of alpha x px plus alpha x, the commutator of alpha x and px. The first term goes to 0, and we know that the commutator of alpha x and px, that is also 0. Hence, the first term in the acceleration operator is 0. We can write it as the commutator of alpha x, the commutator of alpha x c alpha x px is equal to 0. Now let us consider the second term, that is the commutator of alpha x and c alpha y py. This is equal to c times the commutator of alpha x and alpha y py. Now we can represent the commutator as c times the commutator of alpha x y py, alpha x and alpha y, then py plus alpha y, the commutator of alpha x and py. Now we have the commutator of alpha and p is 0. Therefore, the second term is 0. Only first term remains. Therefore, our commutator becomes c times the commutator of alpha x y py. This is equal to c times alpha x y minus alpha y alpha x times py. Now what is alpha I alpha j? Alpha I alpha j is minus alpha j alpha I. Therefore, our commutator becomes C times 2 alpha x alpha y py. Therefore, the commutator alpha x C alpha y py is equal to 2C alpha x alpha y py. Now let us evaluate the third term, the commutator of alpha x C alpha z pz. This is equal to C, the commutator of alpha x alpha z pz. This is equal to C times the commutator of alpha x and alpha z pz plus alpha z, the commutator of alpha x and pz. Here again we have the commutator of alpha and p is equal to 0. Therefore, the second term goes to 0. So only first term remains. Therefore, our commutator becomes C times, within bracket, alpha x alpha z minus alpha z alpha x times pz. Now we know that alpha I alpha j is equal to minus alpha j alpha I. Therefore, our commutator becomes C times then 2 into alpha x alpha z pz. Hence, the commutator alpha x C alpha z pz, that is equal to 2C alpha x alpha z pz. Now let us find out the last commutator, the commutator of alpha x and beta mc square. This is equal to mc square, the commutator of alpha x and beta. This is equal to mc square, then within bracket alpha x beta minus beta alpha x. We have alpha I beta is equal to minus beta alpha I. Therefore, our commutator becomes mc square 2 times alpha x beta. Hence, we can write the value of the commutator alpha x and beta mc square, that is equal to 2mc square alpha x beta. Now let us find out what is the value of the acceleration operator. This is C by IH bar. The first term is 0. The second term is 2C alpha x alpha y py. The third term is 2C alpha x alpha z pz. And the fourth term is 2mc square alpha x beta. This is equal to 2C by IH bar, then let us take alpha x also outside the bracket. Now AX become 2C alpha x by IH bar, C alpha y py plus C alpha z pz plus mc square alpha x, that is equal to mc square beta. mc square beta. We have taken alpha x outside the bracket. This is equal to 2C alpha x by IH bar. Then C, we can add and subtract alpha x px. So within bracket we have C alpha x px plus C alpha y py plus C alpha z pz plus mc square beta minus C alpha x px. Here we have added and subtracted C alpha x px. Therefore, the acceleration operator becomes 2c alpha x by ih bar c into, we can write it as c alpha dot p plus beta mc square minus c alpha x px. Now what is c alpha dot p plus beta mc square? It is given that it is the Hamiltonian which is given in the question. Therefore, the acceleration operator become 2c alpha x by ih bar, then h minus c alpha x px. This is equal to 2 IC by h bar, then c alpha x square px minus alpha x h. Now we have alpha I square equal to 1, therefore alpha x square is also 1. Hence the acceleration operator is 2ic by h bar c px minus ax h. Now this is ax cap, which means that this is the x component of the acceleration operator, that is equal to 2ic by h bar c px minus alpha x h. Now we can write the general formula for the acceleration operator as 2ic by h bar cp minus alpha h. Therefore, from the given option, option A is the right option.